Imagine the night sky, a breathtaking panorama stretching out before you, filled with countless points of light. A vast, dark canvas scattered with stars, each one a sun in its own right, potentially with planets orbiting it. Each a distant sun burning across unimaginable distances, radiating energy and light across the cosmos. They are beacons in the darkness. They seem eternal, but every star has a story, a life cycle from birth to death. Written in the elements it contains, a cosmic fingerprint revealing its origins and evolution. The key to this story is a property called metallicity. It's a subtle but powerful clue. To astronomers, a metal is any element heavier than hydrogen or helium. It's a bit of jargon, but it's important. Carbon, the backbone of life, oxygen, silicon, and more, the building blocks of planets and everything we know. The amount of these elements in a star is its metallicity, a measure of its chemical richness. And it unlocks the history of the cosmos, revealing how the universe has changed over billions of years. After the Big Bang, the universe was mostly hydrogen and helium, a simple and pristine state. Generations of stars have since forged heavier elements in their cores through nuclear fusion, and in their explosive deaths, these elements are scattered across the universe, enriching the interstellar medium. Each star is a time capsule, preserving the conditions of its formation. Its composition a snapshot of the galaxy's history at its birth, a record of the elements available at that time. By studying metallicity, we trace the universe's evolution from simplicity to complexity, from a primordial soup to the rich tapestry we see today. Let's explore what metallicity means in more detail, how we measure it using sophisticated instruments and techniques, and what it reveals about stars and their environments. We'll see how it acts as a cosmic clock, helping us to understand the ages of stars and galaxies, and guides our search for planets beyond our solar system, because metallicity also influences planet formation. The story of metallicity is the story of how the universe became self-aware, how the elements necessary for life were created. Written in Starlight, a message from the distant past. It's the story of how we came to be, connected to the stars in a profound and fundamental way. The early universe was simple, incredibly simple in fact. Imagine a cosmos just beginning, a blank canvas ready for the first strokes of creation. Almost entirely hydrogen and helium, the lightest and most abundant elements. These were the building blocks of everything that was to come, with a trace of lithium. These three elements were essentially all there was in the immediate aftermath of the Big Bang. Where did everything else come from? All the other elements that make up planets, life, and everything we see around us? The answer: stars. They are the cosmic forges where elements heavier than hydrogen, helium, and lithium are created. The first stars, born from pristine hydrogen and helium, were giants, far more massive and luminous than the stars we see today. In their cores, under immense pressure and temperature, nuclear fusion created helium, the first step in a chain of reactions, then heavier elements like carbon and oxygen. These elements, essential for life as we know it, were forged in the hearts of these stellar behemoths. This is the heart of metallicity, a concept that might sound complex but is actually quite straightforward. To astronomers, metals are all elements forged in stars. Anything heavier than helium is considered a metal in astronomical terms. A star's metallicity measures how much of it is made from recycled stardust, the remnants of previous generations of stars. Low metallicity stars are ancient, relics from the early universe, made mostly of original hydrogen and helium, the pristine gas from which the first stars formed. High metallicity stars are younger, relative newcomers to the cosmic scene, born from clouds enriched by previous generations of stars, clouds that contain a higher proportion of heavier elements. When massive stars died as supernovae in spectacular explosions, they seeded the galaxy with heavy elements, scattering the products of their nuclear fusion across vast distances. This stardust mixed with hydrogen and helium in the interstellar medium, the space between stars, creating richer material for new stars and planets, paving the way for more complex and diverse cosmic structures. Metallicity is a measure of this cosmic recycling, this ongoing process of stellar birth, death, and rebirth. It tells us how many generations of stars have come before in a particular region of the galaxy, offering insights into its star formation history. By studying it, we uncover the universe's ongoing transformation, from a simple soup of hydrogen and helium to the complex and diverse cosmos we observe today. Every star's metallicity is a clue to its place in cosmic history, a piece of the puzzle that helps us understand the grand narrative of the universe. Why do astronomers care so much about metallicity? What makes it such a hot topic in the world of astrophysics? It's a crucial clue, a vital piece of the puzzle, to understanding a star's life story and the evolution of galaxies, offering insights into how these vast cosmic structures have changed over billions of years. Metallicity shapes a star's size, influencing whether it becomes a compact dwarf or a colossal giant. Temperature, dictating how hot or cold its surface will be. Color, determining whether it shines with a fiery blue or a gentle red hue. And lifespan, deciding how long a star will burn brightly before its eventual demise. Think of it like baking. More ingredients mean a richer result, a more complex and flavorful outcome. Metals in a star trap energy, acting like tiny barriers that impede the flow of radiation, making high metallicity stars cooler as the trapped energy lowers their surface temperature. Redder and larger as the increased pressure from trapped energy causes them to expand. This chemical difference impacts a star's structure, influencing the layers within and the processes that occur in its core, and how long it shines, affecting its luminosity and the duration of its hydrogen-burning phase. Metallicity also affects how quickly a star burns its fuel, influencing the rate of nuclear fusion in its core, and its ultimate fate, determining whether it ends its life as a white dwarf, a neutron star, or a black hole. By knowing a star's metallicity, we can predict its evolution and end state, tracing its journey from birth to death with greater accuracy. On a larger scale, metallicity maps the chemical history of our galaxy, revealing the distribution of elements created in previous generations of stars. Metal-rich stars cluster in the galactic disk, where star formation is ongoing, enriched by the remnants of previous stellar explosions. Metal-poor stars in the halo are ancient relics from the galaxy's early days, formed when the universe was much younger and less enriched with heavy elements. Studying metallicity lets us piece together the Milky Way's assembly and growth, understanding how it merged with other galaxies over time. It's not just about individual stars, it's galactic archaeology, digging into the past to uncover the secrets of our cosmic neighborhood. Metallicity reveals the story of cosmic recycling and the building of worlds as the elements forged in stars become the building blocks of planets. It's a key to understanding our place in the universe, connecting us to the grand cosmic cycle of birth, death, and rebirth. How do we measure the chemistry of stars light years away? The answer is spectroscopy, breaking starlight into its colors like a rainbow. This rainbow is crossed by dark absorption lines, each a fingerprint of an element in the star's atmosphere. By analyzing these lines, astronomers identify which elements are present and in what amounts. Comparing the strength of metal lines to hydrogen lines gives a precise measure of metallicity. Iron is often used as a proxy since its lines are strong and easy to spot. Astronomers use a logarithmic scale. The sun's metallicity is 0. Lower values mean less metal, higher values mean more. This technique lets us take a chemical census of the galaxy, star by star. Starlight becomes a cosmic barcode revealing the universe's recipe. Metallicity acts as a cosmic clock, marking generations of stars. The first stars, population 3, had almost no metals, born from pure hydrogen and helium. They lived fast, died young, and seeded the cosmos with the first heavy elements. We haven't seen one directly, but their existence is central to our models. Next came population 2 stars, very metal poor but not zero. These ancient stars, over 10 billion years old, reside in the galactic halo and globular clusters. Finally, population 1 stars, like our Sun, are metal-rich and found in the galactic disk. They're the youngest, born from gas enriched by countless stellar generations. Our Sun formed from a nebula rich in elements that would become planets and us. Each star's metallicity tells us when it was born in the universe's timeline. By reading this clock, we trace the universe's journey from simplicity to complexity. The Sun is a classic population 1 star, metal-rich and life-giving. About 2% of its mass is elements heavier than hydrogen and helium. That small fraction made all the difference. It enabled the formation of planets. The Sun was born in a stellar nursery, from a cloud enriched by billions of years of galactic history. Its high metallicity gives it a stable, long life, and its familiar yellow-white glow. Other nearby stars, like Alpha Centauri and Sirius, share this heritage. The metals in the sun's interior regulate its energy flow, allowing it to shine steadily for billions of years. As the sun formed, leftover metals in the surrounding disk clumped together to form planets. Without that 2%, there would be no Earth, no rocky worlds, no us. The sun's metallicity is the foundation of our solar system's complexity. To find the galaxy's oldest stars, we look to the Milky Way's halo. Here, population 2 stars, ancient and metal-poor, survive as living fossils. Some, like He 1327 to 2326, have iron content just a tiny fraction of the sun's. These stars formed from gas enriched by perhaps a single supernova over 12 billion years ago. We also find them in globular clusters, dense swarms of ancient stars orbiting the galaxy. These clusters are snapshots of the early Milky Way, old and red, and chemically simple. Studying their orbits and chemistry reveals how the galaxy formed from smaller pieces. The halo stars confirm the Milky Way's chaotic, ancient origins. Their low metallicity marks them as the galaxy's foundation stones. They are windows into the universe's distant past. Metallicity is key to planet formation. Planets like Earth are built from metals, elements forged in earlier stars. Observations show that stars with higher metallicity are more likely to host planets, especially gas giants like Jupiter. In a metal-rich protoplanetary disk, dust grains quickly clump into planet cores. These cores can then attract thick atmospheres, forming gas giants before the disk's gas is blown away. In metal-poor disks, planet formation is slower and less efficient. Astronomers now target metal-rich stars in their search for exoplanets. While rocky planets can form around a range of metallicities, gas giants favor metal-rich hosts. The chemistry of a star guides the search for new worlds. Metallicity links the birth of planets to the life cycles of stars. The story of metallicity is the story of cosmic creation and recycling. Each generation of stars forges new elements, scattering them as stardust for the next. By reading Starlight, we become galactic archaeologists, mapping the Milky Way's history. Metallicity reveals how the galaxy grew more complex with each passing era. It's also our guide in the search for life, since rocky planets and life itself require metals. The iron in our blood and the calcium in our bones were forged in ancient stars. We are made of stardust, the recycled metals of the cosmos. When you look at the night sky, you're seeing the engines of creation and the story of our origins. Metallicity reveals a universe deeply connected to our own existence.